Well, good morning, everybody. Is it Friday already? Well, it must be because here we are at the Future Panther Academy. Thanks for joining us again today. My name is Bonnie Fugiasco. I work for the UWM Alumni Association where I serve as the Special Events Manager. So welcome back to all of you who have been with us for the past few weeks, and welcome to all the new folks who are joining us today as we present the 6th edition of our 9-week Friday morning series called Stars Have Stories. We're so glad that you're here with us today. We are presenting this program in partnership with the UWM Planetarium, and that's where our program host, Dr. Jean Creighton, she's the director there since 2007, and as an astronomer, she's been hosting the series with us, and she's got another great program for us today. So today's episode is called How Hot Can a Star Be? And just so you know, you can send your questions to Dr. Jean. There's a little chat box on the right of your video screen as you're watching us today on YouTube, and we'll get to just as many of those questions as we can. Just a reminder, if you're looking for previous programs that you may have missed or you wonder what's coming up next, look at the UWM Alumni Association website, and you can find links to everything there, and you can watch it live on demand anytime you want. So with that said, let's all settle in, get comfy, and let Dr. Jean take it away with this week's episode, How Hot Can a Star Be?
Thank you, Bonnie, and thanks everyone for being patient. Think now about something much bigger than the internet capacity that we have when everybody's Zooming. Let's think about how do we measure stars' temperatures? When they're so far away, how do you even do that? And I guess one of the ideas we're going to need to talk about is that the temperature of a star depends on its color, or I should say, the color of a star is influenced by its temperature. In our regular life, when we think about hot, we usually think about red, and when we think about cold, we think about blue. But stars are in opposite land. Stars are really hot when they're blue and really cool when they're red. And it turns out that's a really important, perhaps one of the most important pieces of information about a star, its temperature, because it tells us something about its brightness. So we're going to look together at probably the most important way of describing properties of stars. Let's go ahead and do that. What we call the x-axis, so the lower axis, is where we're going to put temperatures. And notice how the red temperatures are cold on the right, and the blue is on the left. That's where stars are really hot. The numbers that you see go from 3,000. I know that sounds hot, and it is hot, but we're talking about stars after all. And it gets hotter and hotter and hotter and hotter until you get to 30,000 degrees Kelvin. You might never have heard of Kelvin. You might have heard, of course, of Fahrenheit or Celsius. Kelvin is a great unit because 0 Kelvin is when nothing moves. Even the protons in your body, your electrons, have all come down. They're so cold, they're kind of frozen. Think about that. So it's a cool unit to have, Kelvin. Now the other axis is going to be the brightness, and the fancy word for that is luminosity. It tells us how much light the star makes. Our reference point here is going to be the sun. So the sun is sitting at 1. That means 1 is the brightness of the sun. That's our kind of our measure, our ruler, if you will. There are going to be stars that are much brighter than the sun. So you'll see hundreds or even tens of thousands of times brighter than the sun. Think about that. There are stars out there that are thousands of times brighter than the sun. But there are also stars that are dimmer, much dimmer than the sun, hundreds of times or even 10,000 times dimmer than the sun. So the sun is kind of squarely in the halfway. So now we're going to think a little bit because I want you to guess. I want you to predict. If we're looking at a hot star, is it going to be brighter than the sun or dimmer than the sun? So if we're looking at a star that's hotter than the sun, is it going to be brighter or dimmer? What would you guess? And I'll give you a few seconds here to think about that. Would a really hot star, would you expect it to be brighter than the sun or dimmer? And I'm hoping that you chose brighter, although any guess is good because it informs our ideas, but any very hot star is going to be brighter than the sun, typically. Now, thinking along those same lines, would you expect a much cooler star than the sun to be cooler star to be brighter than the sun or dimmer than the sun? Again, we're expecting that if it's really much cooler than the sun, it's going to be dimmer. And by the way, we call these stars right here on the lower right-hand side, we call them red dwarfs because they are red in color and they're all over the place. They're really abundant. Most stars are going to be in that category. Let's connect everything. Let's put all the stars with all the temperatures across the board, and you see a nice straight line. And the term that you're going to see here is main sequence, which is a code to say adult. These stars are adult stars. They're burning hydrogen into helium, as we've talked about before. You smash basically protons into in very hot, dense environments, and they hook up together to make helium. And that releases energy, and that's what makes stars shine. This is where 90% of a life of a star is spent, right there on the main sequence. Okay, is that it? Not quite, because it turns out that off the beaten track, we're going to find stars that are overachievers and underachievers. Let's look at the overachievers first. I'm hoping you notice that in this group of stars that we call giants and supergiants, there are going to be some stars that we've talked about before, or maybe you've heard before, like the pole star is also what we call the North Star. You've probably heard of Betelgeuse. These are stars that are really bright in the night sky. Rigel is also in Orion, like Betelgeuse is. So why are these overachievers? They're overachievers because these stars are cool. Look at Antares, for example, a bright star in Scorpius. This is a really cold star at 3,000 degrees. So why is it so bright? It looks like it's 10,000 times brighter than the sun. Why is this star so bright? And I'm hoping that you get the hint from the names of these. These are classes of stars, giants and supergiants. What's different about them? Not the temperature, something else. It's going to be their size, right? These stars are huge. So although they're cool, and that means that per unit area, they don't really produce a lot of light compared to hot stars. There's so much of the star that if you take all of that together, it makes a lot of light, and that's why they look so bright. Those are the overachievers, right? The giants and the supergiants. What about the underachievers? These are stars that are hot, and yet they just don't make very much light. And the reason for this, again, it's a hint from their name. They're called white dwarfs. White because they're hot, but they are dwarfs. They are small stars. Some of these white dwarfs are going to be the size of the Earth, much, much smaller than the sun. And the only star you probably have ever heard of the white dwarfs is the companion to Sirius. Sirius is the brightest star in the sky, and next to that really bright star, there's a little companion. And if you use a good telescope and block the super bright star, you can see an itty bitty little white dwarf. The first time we managed to do that was in 1940. This, therefore, this graph that I'm showing you is probably the most important graph in astronomy. And here you have it on a Friday morning on a beautiful day in May or whenever you're watching this. So let's recap. We talked about how the temperature of a star determines how bright it is for most stars, because most of stars spend their time as adults, and that basically is going to fix their brightness. Now you might say, well, why are some stars hotter than others? And that has to do with their mass. The low mass stars, like those red dwarfs, low mass stars, all over the place. And really high mass stars are going to be more rare, but those are the ones that shine. They're hot and they shine at great distances. So let's talk a little bit about the other idea that I mentioned about how stars are different in size. So their brightness depends on their temperature, but also how big they are. And we think of the sun as being super big because it just looks so big in the sky compared to other stars. But really, if you were to line all the stars together, the sun isn't all that big. Notice how Sirius, for example, the brightest star as it appears to us in the sky, is about 2 times bigger than the sun. By the way, notice how the planet Earth is not even visible compared to the sun. You can barely see there Jupiter and Saturn. Earth is just too small on this scale. So let's back up a little bit more and look more past Sirius. Pollux is one of the bright stars in Gemini. Gemini, remember, looks like twins. And if you can wiggle your finger like this, I can barely do it. That's one of those bright stars of the twins. Arcturus is a star I've mentioned before, a star we grabbed from another galaxy, which is why I like to call it an alien star. That's a red giant. Keep going to Rigel. Rigel, notice how big. It's almost 100 times larger than the sun. And really, you can keep going, and I'll just tell you that the biggest star that we can see is UY Scuti. And it would take you, if you were on the fastest plane we've ever made, called the Blackbird, it goes over 3,000 miles an hour. It would take you 40 years to go around the star once. Think about that. It's hard to even imagine. These really large stars, because they're so bright, we can see them at great distances. And you can talk about light years, but we thought it might be fun to imagine that 1 light year is a mile. And what would that look like if you plop these stars on a map of our region in Milwaukee? We're going to put the sun at the Manfred Olson Planetarium at UWM on the east side. Sirius would be at Miller Park, about 9 light years away. And then we'll find the next star, Arcturus, 37 light years away, all the way in Kenosha. Aldebaran, one of the big giant red stars, is in Fond du Lac at 65 light years away. Think about how easy it would be to see a star if it was parked in, say, Memphis. That's Betelgeuse at 642 light years away. So Atlanta, Rigel, 860 light years away. So Rigel again is in the constellation of Orion. And here it is, UY Scuti, the star I said that's the biggest one we've seen so far, is in Athens, Greece, my hometown where I grew up. 5,000 light years away. It kind of blows the mind that we can see a star that is that far away. So that gives you an idea of we are able to see stars that far, individual stars, because they are so luminous, so bright, and so large. So with that wonderful thought, I think we can talk about the questions that you have, and I'm always happy to get your questions because they're so good and they help me elaborate to talk about things that I love.
Wonderful. Thank you, Dr. Jean. So our first question today comes from Candace, and she would like to know, what is the coolest star we know of?
Great question, Candace, because the answer to this question is changing over time. Like every year we find a cooler star, and now we're getting to this embarrassing situation that the coolest star we know is about as hot as a hot cup of coffee, like at 200 Fahrenheit. And that even makes us wonder, well, is that a star? You can't have fusion in a star that's cold, that cold. These are called brown dwarfs, stars that haven't really pulled themselves together to make light, but they're still interesting. So think about that. A star you could almost touch. That's how cool they are.
All right. Our next question comes from James, and he asks, what is the hottest star near us other than the sun?
The hottest star is going to be Eta Carina. Eta is the, I think it's the 8th letter in the Greek alphabet. So it's the 8th brightest star in the constellation of Carina. And that star is 70,000 degrees Kelvin. So that's off the graph that I showed you is almost twice as far to the left as what I showed you. Very, very hot. Thanks, James, for your question.
All right, and our next question comes from Alex. What happens if a star gets too hot or too cold?
Well, what happens? Let's see. If a star gets too cold, it ceases to be a star in a technical sense, because to be a star, you need to be hot enough to force protons to come together, to smash together and make heavier elements. If you can't do that, technically speaking, you're not a star. So you're a wannabe, right? That's what happens if you're too cold. If you're too hot, that means that you are slamming things so successfully that you get to iron. And if you start slamming iron together, the star becomes unstable. And as we've seen before, it explodes into a supernova. So you cease to be again. Being too hot or too cold for a star is a dangerous business. Thanks
All
for your
right.
question.
That was a good question. All right, Evie wants to know, do the stars' temperatures change and why?
So Evie, I'm really pleased you asked that, because I realized that I didn't really talk about the fact that stars aren't parked on that graph forever in one spot. They move around because the temperature that we're measuring is of the outer layers of the star. We can't measure easily anyway. We can't measure the inside of a star. So if the star starts changing its size, either getting bigger or smaller, and it can do that as we will talk about next time, as it gets bigger, the outer layers are farther from a heat source, which means that they can get cooler. So a star's temperature can change over time, either to the cooler or to the hotter. And that's what's going to make the same star jump around in different locations on the diagram that I showed you. That's an excellent question. Thank you.
Mm-hmm. All right. Let's see. Our next question is from Katie, and she wants to know, who chooses the names for stars?
People ask me that all the time, Katie. What a great question. So some stars you've noticed already have names, like Sirius, like Bob, right? They have names. They might not be names you use every day, but they do have names. And I should point out that most stars' names are from the Arabic. A few are from Greek, but many of them are Arabic names. Now, you couldn't possibly sit there and spend all your time saying, okay, this is a name, and that's another name, because nobody would even remember, nor would it include any information. So what people did was they said, how about we name stars in a way that tells us something about the location and the brightness of the star? So let's say this star is in this constellation, like Sirius, for example, is going to be in Canis Major. That's the official constellation of the big dog. And because it's the brightest star in that constellation, it is named after the first letter of the Greek alphabet, which is Alpha. So you would say Alpha, which fixes its brightness in that region of the sky, and Canis Major to say, up, it's in that particular kind of section of the sky. But what's interesting is even that becomes not enough. Too many stars, not enough time. And what if this star is the 300th brightest star? We run out of letters, right? So then what we do is we say, okay, here's my catalog, the NGC catalog. It's going to be the 42, 36, 52, that kind of number. And that tells you the entry in the catalog of a star. There are many catalogs. So that also means that if you put that name in the internet, it'll give you every piece of information we have about the star. So for practical purposes, it's nice to have a simple name that is just, here is a code that I can use to get everything we know about that star. Great question, Katie. Thank you. And I should say, I think this is our last question that we have time for today. I just wanted to mention that next time we're going to talk about how stars are born. I know that you've asked me about this before, and we'll kind of connect back to some of the ideas that we've talked about before. How do the properties of a star change over the course of its life? Thank you so much for listening, and I look forward to chatting with you next Friday.